Okay, so far, the most upsetting part of this class has been where I get to this page, and it's like, oh, okay, we're going to do uniform circular motion, which basically means, first of all, imagine you're just like on a set string and you're just going whoopie, 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 whoopie. Or if you're on those, like, I don't even know if they're allowed to have them in playgrounds anymore, but your friends would like run them really, really fast, and then you would barf and everyone would laugh and it'd be great. But anyway, it's a spinny thing. If you're spinning on a fixed axis. Okay, so your book does this thing, and it's like, blah, clearly, blah, and you're like, oh, okay. And it just says, we can find it from, which, like, it's hiding all the cool math from you, and it makes me so sad. So I have this other video where you do all the cool math, and you should totally watch it so you can learn where this actually stupidly comes from, because for real, this is a big deal. Like, so we just like casually in this class go, well, the acceleration is v squared over r, and you're like, well, what v and what r, and where did you come up with that? And like, it really comes from calculus, and it comes from the fact, remember how whenever I was like, you've got this velocity, which is the ddt of x, or over the position or whatever, r I think I called it, but r is really, x component I hat plus y component j hat plus z component k hat, and really if you're going to take the derivative, you have like the derivative dx dt I hat plus x derivative of I hat dt. Okay, and then we're like, but we're just going to pretend that's zero, and we moved on. We have more stuff to go with that. Well, this whole v squared over r thing comes from this thing, which is bonzo, and it's so interesting if you're a super dopey dork, and honestly, you kind of should be because you're taking physics. I mean, you're not taking this for no reason. You're like, what I'm going to do with my free time? I'm going to take a physics class. I mean, no one's making you take this class, so obviously you're cool somehow. Anyway, there's all this really cool stuff that goes into where this equation comes from. There's this whole other video I made to go into it. But basically the idea is TLDR, if you're going around in a circle, TLDR, too long, didn't read. If you're going in a circle and your radius is constant, this is super important. And these are all those things, those assumptions that you make if you're doing the derivation. And that's why I get really sad when we don't do derivations in class, is because the derivations is where all the cool stuff is, because that's where all the assumptions are. And if you don't know what the assumptions are, then you don't know why the... Honestly, I feel like I didn't understand physics until I took the class where we actually went into like breaking all the assumptions, and I was like, oh, well, that's why we did that there. So I think that's what I'm trying to make up for. Okay, so if we have a constant radius, then this isn't just a regular acceleration. Okay, this is the acceleration into the center. So let's say, hold on, I'm going to try this better. So let's say you're going like 30 miles per hour, and you're going like 5 feet. Okay, well, first of all, I have to convert miles per hour and feet. I'm using miles per hour and feet because I feel like that's stuff that we already know. So let me convert everything to meters and seconds. So I'm going to be super lazy, and 30 miles per hour to meters per second, 13.14. So this is 13.14 meters per second, and 5 feet to meters is 1.54. 1.524? I already forgot. 1.524. Okay, 1.524. So what this acceleration is basically saying is that acceleration toward the center is going to be v squared over r. Okay, so that's going to give me 13.14 squared divided by 1.524. So an acceleration of 13.1. Basically, these are all fake numbers anyway. So let's say I'm experiencing 113 meters per second squared acceleration. Well, what does that mean? Okay, so somewhere in your history of science, you might have heard something like I'm not going to put that sign there. F equals ma, like force equals mass times acceleration. So let's pretend that you weigh, I don't know, 180 pounds. So 180 pounds to kilograms. So let's say you weigh 82 kilograms. So if I weigh 82 kilograms and I'm experiencing an acceleration of 113 meters per second squared, then that means I'm experiencing a force of, I'm experiencing a force of 9.2 newtons. So, or 9,000, I already forgot what that number was. 9,290 newtons. Whoa. Okay. So, these are newtons. This is a measure of force. We talked about that. Now, because I don't really understand what newtons feel like, I'm going to go with 9290. What was it? 9290? I'm terrible at remembering things. 9290 newtons to pounds. So that's basically meaning that you're feeling a 2,000 pound force. Like, you know, if you're sitting in a chair, you're going to go, whoo, and you're going to feel a 2,000 pound force. Because if you're going 30 miles an hour on a 5-foot radius, that's actually like super duper fast, right? Does that make sense? Like, just to compare, if I'm going 30 miles an hour over like a 30-mile radius, let's see how these numbers would change. Like if I'm going 30 miles an hour, sorry if you grew up with metric, and we're going in like a 1-mile radius, then we have our acceleration is 3.14 meters per second, 13.14 meters per second. And 1 mile is how many feet? I should know this. I'm tired. 1 mile, 2 meters is 1609, of course. So 1609. So the speed, so basically what you're dividing by is kind of a big deal. So 1314 squared divided by 1609, and then that, so your acceleration now is only 0.107 meters per second per squared, meaning your force, again, if you're 82 kilograms, if we go times 82, your force is only 8.799 newtons, and if I convert that to pounds, 8.799 newtons, 8.799 newtons to pounds. Thank you. To go back to this. Whoa! Come back. 8.799 is only 2 pounds. So you see, that's a huge difference. I mean, that's also a huge difference in... So basically the idea is if you're going the same speed, and you're like, I know this already, why did you do all this? If you're going the same speed around a tiny, tiny, tiny radius, you're going to feel a 2,000 pound force, depending on your mass. If you're going around a 1 mile loop, you're basically going to feel nothing. Okay? That's the importance of this. So the faster you go, that's important. The further out you are from the center, that's also important because that's what you're dividing by. Okay? So this v squared over r, that's referring not to the force itself, because notice that every time I did this, I did mass times acceleration. I always multiplied it by a mass to get to a force. This is just the acceleration. So basically that means to keep you going in that circle, you have to be accelerating toward the center. And this is a really weird concept. So another way to think about it is like, let's say if I was on a string and I was going here at 30 miles per hour, and what did my acceleration here was, oh gosh, what, 0.07 meters per second squared. I don't know what that is. 0.107 meters per second squared, 2 miles per hour squared. meters per second. No, I can't do that. Oh well, we'll just do it. I'll just do it in miles per hour. So if I was in per 1 mile. Okay, so my acceleration is 900, right? Because it's 30 squared over 1. Miles per hour squared. So basically what that's saying is I always got confused whenever I studied this in physics, because I was like, well, that just means, why does it say that I'm accelerating toward the center? Because I'm clearly not going toward the center, because I'm never hitting the center, I'm always off. But what that means is at this instant, I have to be changing my direction. So acceleration is a change in direction. Okay? So if this string broke, I would go this way forever at 30 miles per hour and nothing would ever change again. Okay? The only thing that's changing is the tension in this cord is putting that force of like 2 pounds or 2,000 pounds or whatever pounds, we were talking about. The tension in that cord is that force that is holding me in to keep my velocity solid. So basically the idea is, remember we talked about how the two directions are separate. So at any given point on a circle, I'm going this direction at 30 miles per hour. But my acceleration is changing my velocity. So originally I had 0 velocity in this direction, but I have an acceleration of 9,000 miles per hour squared in that direction instantaneously. So I would be like, oh, okay, so it's 9,000 times teeny tiny time plus 0. Because my initial velocity in that direction. My initial velocity in that direction is always 0, but it's teeny tiny t. At every single one of these points, it's 900 times teeny tiny t going in that direction, which causes the whole arrow here to change direction just a little bit so that it ends up going in a circle instead of in a straight line. I feel like I'm doing a terrible job of explaining this. It's just basically saying that this is what makes us go in a circle. If that didn't exist, we would go in a straight line forever. So if I'm in a car and I hit the accelerator and I have an accelerator where I'm increasing my miles per hour squared, if I'm accelerating, this is totally different from my v squared over r. So if I'm going around in a circle and I'm accelerating, that has nothing to do with my v squared over r. The v squared over r is the thing that keeps me going in a circle. It's that tension in the rope. It's that vector that keeps me pointing toward the center that keeps getting added instantaneously in that teeny tiny t. So 900 times teeny tiny t makes me go toward the center so that I have this curvature. It's a very, very weird way to think about it, and it's okay if you don't get it yet, because really the whole point is just that we're going with the acceleration is v squared over r, and that's probably all you need to know for right now. But it's very odd, and we spend a very, very deep amount of time in it in dynamics, and here we spend one part of one chapter on it. So I just wanted to give you a little bit of thought behind it about where we come into it, and then we'll go work a problem or two.